All right, so I turn it on to get it spinning. Make sure everything's connected and touching. Get my measurements up on my scope here. All right. And like so. And so there we go. So now on my computer screen, I can see, if I can pull that out a little more. On my computer screen, I'm watching the speeds of things to see how they're changing as it speeds up.
Okay.
Right now, the starting speeds, I have the, let's see which one's which. I have the top disk is going at 27 hertz, 28 hertz, which is about 1680 RPMs. I have the bottom disk going at 24.5 hertz, about 1470 RPM. And after I turn it on, I just gotta wait a little while because there's an eddy current in the middle disk that is taking a little while to speed up. Now, one thing I can do while we're kind of waiting, I can demonstrate something. So when you take a piece of aluminum and you have the aluminum move very fast past a magnetic field, it'll induce eddy currents in that aluminum. I can perform that with this guy. Now when I bring this guy close to the spinning disc, it's going to slow down the speed of the disc. If we're quiet, we might even hear it slow down.
Yeah. Oh, that slowed it down considerably. Okay.
Yeah, see?
So it's inductance.
Yep.
So again, just to point this out for anybody who doesn't watch the other videos, right? So you have an ultrasonic buzzer on top. These are the power leads for the buzzer. So these are coming in there. You have a high voltage source coming in. Positive, going to the top clockwise spinning disc. Yeah, at plus 10 kV. And there's a brush there. So it comes in here, goes down to the brush. You can see a little bit of sparking when the lights are off. You also have a power return. You have the negative down here, and the camera's not going to see this. But you have a negative down here at another brush on the bottom disc. So your field gradient then is going to be between the top disc and the bottom disc, and you've got this metal plate in between them. Correct, and the metal plate is an AC signal from the Tesla coil at a couple of kV at about a megahertz. And then you got, is your finger okay? Yeah. Okay. You gotta be careful of these spinning discs because they got screws sticking out on the bottom to hold those magnets, and if you get your fingers too close, it'll snag them. So yeah, you got this high voltage static electric field on these spinning discs. And then you have this AC field in the middle of these two discs. So these two discs are acting like flat plate capacitors, right? A flat plate capacitor has a positive and negative side. The difference is that we've added angular momentum into there. So now these charges on these flat plates are rotating to each other. When you rotate and move charges like that, you induce currents. You're creating magnetic fields. Well, it just so happens on one of these flat plates, we've got magnets on there to amplify how that rotation of the charges is creating a magnetic field. So we're creating an even stronger magnetic field by putting these magnets on there and putting a high voltage charge on those magnets that's moving around really fast. So that amplified magnetic field creates this eddy current in this center disc where we have this Tesla coil high frequency signal coming. When you run a high frequency signal through a conductor, you start working with something called the skin effect. The skin effect. So the Tesla coil, I should just point this out, the Tesla coil comes into the frame here, so it's being applied to the entire thing. So yes, the way the original inventor did it is he did not isolate these vertical rods from the center plate, but he did isolate the motors from the frame, right? Okay. So I've somewhat replicated that, but with just even more insulation by using these 3D printed horizontal struts here.
So the signal from the Tesla coil is going to the center disk. It's also going to these vertical rods. Right now, as it stands, we're not sure how much these vertical rods, their characteristics, comes into play for the overall lift effect.
Yeah.
But I've done some analysis on the different craft that Alexey's made, and it looks like he has some very interesting ratios that he uses with these vertical rods. The length of vertical rod that he uses seems to be related to the diameter of the disc, the large disc that he's using.
Okay.
So by putting this Tesla coil signal into the center disk, you start dealing with this thing called skin effect. Skin effect is essentially when you run a current through a conductor, the higher the frequency of that current, the less of the center of the conductor it'll use, and the more and more of just the outside edges it uses. When you use less surface area of a conductor for your current, it takes more energy. You get more resistance to push that current through. So skin effect is something that normally most engineers try to avoid the skin effect, because you're just losing energy in the form of heat through this added resistance. But in this case, I think we are utilizing the skin effect to our advantage, because current creates a magnetic field when it runs through a conductor. By putting a high frequency current through this center disk where the eddy current is already going through it, we're taking that eddy current, we're separating it into two components, the top half and the bottom half of this center disk. We're splitting it into two very thin eddy currents that are only 60 to 70 microns thick, right? So instead of 1 millimeter or 1,000 microns, we're using just a fraction of that for all of that magnetic field. Since you're splitting that eddy current into two components, and you have these top and bottom disks counter-rotating, it's almost as if you're separating that eddy current into two different spins within the single conductor.
Okay. Yeah.
You're creating a layered magnetic field within this 1 millimeter thick aluminum disc. So I believe that the lift mechanism for this whole craft, it doesn't happen in just one place, but it's this interaction between multiple things that's all starting to come together. This piezoelectric buzzer on top, right now it seems as though that piezoelectric buzzer is creating a change to the electric field at the top of the craft that then gets propagated down and starts affecting that separated eddy current in the center disk.
So I should mention on the scopes, and again, those aren't really visible, but on the scopes that you've showed me, when you, if I remember correctly, he has the buzzer on, and then you turn it off briefly, and what Alexey described was a change in the signal, and you've measured that on your scopes. Correct.
When Alexey is getting this thing all tuned up to the state where he says it's ready to take off, the second to last step he does is he tunes the frequency of the buzzer. But by tuning the frequency of the buzzer, you're actually changing its electrical characteristics too. You're changing its capacitance, you're changing its resistance, you're changing its reflectivity ratio. There's a lot of different things that happen when you just adjust this one little knob for the frequency of the piezo. And Alexey, he changes this knob, he changes the frequency of it, the other characteristics of it, until he starts hearing what he calls the special sound. And the special sound he describes as the sound of a fishing reel unwinding. There's a lot of different things that could be. We've tried catching it on camera many times. Unfortunately, we have not yet been able to actually get a decent recording of what that special sound is so that we know what sound we're looking for. Now, and I should mention that we did some testing on this the other day, and I did hear resonance sounds, right? Not just the change in piezo, but so there are different sounds that you've described. We may hear them today. You've described a magnetic grinding noise, and that is basically because you have the two counter-rotating fields, right? They're going to change the way that the motors interact with each other, which is actually interesting. There's actually drag on the motors from the inductive change there. The other thing you mentioned was, going back to the piezo,
I heard some resonance effects that were different frequencies. So that piezo is having some kind of an effect on the system when it's turned on, when it's emitting.
Absolutely. The piezo itself, so I've observed over a dozen different special sounds that it could be, which it kills me, because how do I know which one he's talking about? One of the special sounds I've observed comes from the piezo when you have a very high amplitude on it. On the back side of the piezo, you'll start getting a lot of arcing and sparking in the crystal itself. It is visible. Well, if you have arcing and sparking in this piezo, that's an electric field.
Okay.
If you put that electric field above, on top of all these other interacting fields, you're going to start influencing those fields. So, and it just so happens that the buzzer is making a special sound when it's doing that arcing. There's the mechanical resonances, like I just showed earlier with this magnet slowing the disc down. There's certain mechanical resonances that can sound like that.
Yeah.
Alexey has dropped some hints. He says, or he said one time that he said to us just one time that the speed of the disc will change when it's that special sound, that it's actually the sound of the disc speeding up.
Okay.
Which, if that's the case, there's only one thing that can cause that disc to speed up, and that's a change to the eddy current that is currently keeping its speed down. So if somehow you take those two eddy currents in the center disc and you flip the polarity of one of them, you're going to, all of a sudden, you're going to change the drag, because there's a secondary eddy current in this top disc. Well, if you flip the polarity of this bottom disc, there's going to be a delay between when that polarity, magnetic polarity of that eddy current flips the polarity in the top disc. The top disc polarity is going to have a couple of millisecond change time. And in that couple of millisecond change time, if you have the frequency of the buzzer set just so, when you hit the button, the make it lift off button, you can pulse the electric field such that now you have changed the magnetic polarity of the top disc at the same time that you have changed the polarity of the center disc.
Yeah.
And now you have a pushing force rather than a dragging force on this top disc, causing it to accelerate.
And again, you've measured this on your scopes, and you also have, I mean, for anybody who isn't aware, you have a massive spreadsheet. We're talking hundreds of rows and columns, and you have been mapping and tracking and trying to identify all the bits and pieces. And so it's not like a total fly-by-night effort. The thing that's really impressed me about your work is you're doing very precise measurements on a very complex system, and you're trying to identify what the pieces are that work together. And if this thing does someday fly, you know, it will probably be the result of a very complex interaction that involves several different components to a waveform, I guess.
So going through Alexey's numbers for the spacings of these discs, as well as the diameters of the discs, one common thing that I've been able to note from that spreadsheet that I'm using is that it appears as though he is using either the third and fourth harmonic of the wavelength in air, or the sixth and eighth harmonic of the wavelength in air for his spacing distances of these discs.
Okay.
But he told us that there's some relationship between the ultrasonic in order to determine the proper spacing. So if we combine those two, my observation and what he told us, it seems as though the diameter of the piezo buzzer is strongly correlated to the distance of one of the two rotors, which is strongly correlated to the wavelength that you're using for these ultrasonic frequencies. That information helps tell us what vibrational modes we need to achieve in order to replicate the vibrational modes that he is using in order to create lift. This tells us that there's some secret sauce, some magic within these specific vibrational modes, these specific frequencies, and these materials that Alexey's using to be able to achieve lift.
So, and again, just to put it out there, you don't have lift yet, but have you seen any other anomalous effects? Like, have you seen laser deflection that might indicate some kind of a change in gravity or something along those lines?
So I haven't seen vertical lift, but just a few weeks ago, I got horizontal deflection. Now, you can see on camera, if I change the speed of this,
Yeah.
increase and decrease the speed, you'll see that it rotates clockwise and counterclockwise, right? So that's cool. That's just counter rotation.
Yeah, and that's well understood.
That's well understood. Well, what I recorded and uploaded, this whole thing, instead of rotating clockwise, counterclockwise, I got it to start swinging in one direction, which is a really interesting thing. Unfortunately, or fortunately, I'm not quite sure yet, that is all gyroscopic effects. Slow that down so it's not so loud. There we go. I was able to determine that it's that beat frequency you can hear right now, which is the magnetic grinding of the two interacting
that's the grinding
fields.
noise. Yeah.
I was able to correlate that to the swing. So every time it grinded, it was producing a thrust, but it was producing that thrust in a singular direction. It wasn't producing it, you know, in a rotational form. So I was getting angular to linear conversion, which that alone, if anybody who's familiar with physics can tell you that converting angular momentum to linear momentum is no small thing. So let's see if I can achieve some resonance states here. Close to this so you can hear it.
Okay.
So right now on camera, it probably shows up as a much slower waving motion. But right now, these vertical struts that I have are vibrating really fast.
Okay.
And those vibrations are kind of matching the vibrations of the center disc right now. Because right now, we have a difference in speed between top and bottom disc of about, let's see, about 6.5 hertz, which is about 400 RPMs. So that means that right now that eddy current has a 400 RPM difference between what's creating the eddy current and what is fighting the eddy current on the top. And what's fighting it, that creates a beat frequency.
Okay.
That beat frequency is probably very important for this whole thing.
Yeah, and again, there's a grinding noise going on, and that's a resonance between the two plates and the vibration.
Correct. So right now, I have it set up so that the speed of the discs and the speed of that eddy current is matched to the physical characteristics like the diameter and thickness of the center plate and the stiffness of it, which I'm trying to see if I can make a good way to show just how much this thing is vibrating. So by holding a little piece of metal to the edge of this metal disc where it's vibrating the most, gives you a little indication to how much it's vibrating.
Yeah, and unfortunately, I don't think the camera will pick this up, but yeah, there's definitely a vibration there. So the plastic armatures are vibrating, the whole thing vibrates.
Yep,
and you've said that that's actually required, you think?
There's a couple different hypotheses out there for the mode of lift, for the mechanism of lift. One of those that I think holds some promise is anisotropic damping, or asymmetric damping. There's a lot of different words for it, but the idea is that you're damping the motion in one direction when it swings one way, but then not damping it when it swings the other way. So it's like it's bouncing and then slowing, bouncing, slowing, bouncing, slowing. It's a ratcheting effect.
Ah, okay.
And so you may be able to use that ratcheting effect in order to create a ton of tiny little impulses forces, right? You don't need to create 10 newtons of force to lift this thing up, 10 newtons per second, if you can create 0.1 newton per millisecond would equate to 100 newtons per second.
Yeah,
so
that's I think so. Tom Vallone has written a fair amount about that. That's I think what they call Jeffemenko effect, and in that case it was spark discharges, and he felt like there was an asymmetrical propulsion from a spark discharge. So it was a bunch of little. You'd have a bunch of little impulses.
Yep. So now that I have it set up in this particular resonance state where everything is vibrating and we're getting a nice hum from the middle plate because it's vibrating so hard, I'd say the amplitude of deflection for the middle plate at maximum, about halfway in between a vertical rod and the halfway mark up there, so like a quarter of the way between the vertical rods, that's where you got maximum amplitude of deflection. And it looks like that's about 2.5 to 3 millimeters of deflection.
Okay.
Which, if I pull out my force gauge, we can see how much force that is, right? And that amount of force is about a kilogram worth to make it deflect that much. Well, we know that this thing is deflecting at a couple hundred hertz, probably 400, the difference in speed between the two.
Yeah.
That's 400 times per second. That means that this thing is doing a kilogram worth of force 400 times per second. If we can extract just a little bit of that through this asymmetric anisotropic damping, that means that you're able to create potentially, even if it's 1% of that, you're creating 1% of a kilogram 400 times per second.
Okay, so in that case, then that would be a Mach effect thruster.
It's a modified Mach effect thruster because, and I've talked to the Mach effect guys about this, in their device, they are not using electrostatics at all for their damping. They're using a piezoelectric, but they're just using it to create the physical motion. What I'm suggesting is that you can use the magnetic effects and the electric effects in order to provide damping or acceleration in the two different directions. So instead of just this, instead of just damping one way and not damping the other way, it's damping one way and accelerating the other way.
Yeah. So I think in what you just discussed, this goes to one of the real challenges. This is kind of, because it's ground up, you're starting with the thing and trying to analyze it. There are many different possible modes of propulsion, right? So Mach effect, that's basically mechanical, physical, or at least for the most part, you know, whereas some kind of a field effect would be very, very different. Okay. Yeah, and as long as we both stand about where we were, I think we're good.
Yep.
So.
And you're going to want to keep just about 6 inches more distance. Yep, right there. Because how far away you are from the thing is going to affect how much RF radiation you get. And if you test this for a while, you'll start getting a headache.
Yeah.
And that's why I have my tinfoil hat that I wear when I test for many hours on end. It's actually a silver infused nightcap that's for RF protection, but it looks quite silly.
So one of the downsides to this is there's a ramp up time for this. You have to run the motors, you have to get it into kind of a synchronous state.
And then after you got that, and it takes about 5 to 10 minutes for that, then you have to start charging your parallel plates, your spinning discs, and the charging of that is not fast. You can't just apply the voltage. It's RC constant for the charge time of these parallel plates is about 10 minutes. That's how long Alexsey says that he usually waits before he is ready for the next step, which is turning on the Tesla coil. So once you have these charged plates, then you can start applying the AC field between those charged plates.
Okay.
So I'm right now going to just slowly increase the voltage over time to these spinning discs, which is going to change the speed of those spinning discs. Which means you have to wait even longer before everything evens out again. vibrating any closer to the camera.
Okay. Yeah, and I have so that it's still got you, but you're almost out of the frame.
Okay.
So I can move it if you need.
Can it pick up the screen at all?
No.
Unfortunate.
You're right on the edge of the screen. It's really focused on this, so. Yeah, so you have to go closer. You have to work on your headache.
I'll just keep slowly increasing the voltage here over time. Right now, I can see that the speed of the bottom disc is oscillating, which means that my resonance state is not quite perfect. It means that the eddy current, because I have them spinning very fast right now, and the faster you spin it, the more it amplifies any variations with that eddy current. So right now that eddy current is stronger because it's faster, but it's also causing some added resonance modes, physical vibration resonance modes of the discs. So as I slowly increase the voltage, I'm hoping that that's going to go away or even out, as the electrostatic fields start overpowering the magnetic fields that are causing it in the first place. Now, because I have it at the speed I have it, and everything's vibrating.
Yeah, there we go.
And it's really, it's loud with all these.
Right there is good.
Okay.
Or, yeah, a little bit closer, but.
Because this is vibrating really loud right now, I have everything set up really on the edges of the margins of running right now. It means, hopefully, that as I increase the strength of this electric field, we're definitely going to start noticing some changes to this physical audible vibration.
Yeah.
And that's very helpful for tuning, because if you're trying to see what parts affect what parts to help you tune it, it's good to run it up on the very edges of the margin, really fast. The tiniest little change will make a big difference. Well, we'll keep on testing it at the very edges where my tiny changes will make very noticeable differences. So the speed of the top disc has already started to slow down as this electric field of the charge that is being stored on that top disc is now interacting with the magnetic field of the eddy current in the center disc. So it's this electrostatic magnetic drag, right? Before we just had magnetic drag that was causing a beat frequency. Now we've added in another layer, which is electrostatic interactions with that magnetic field. And it looks like we're already starting to slow down in the vibration or the changes in speed on the bottom disc, which is a good thing. We want everything to be as evened out in its speed as possible. You don't want large changes in speed constantly, because that's going to make tuning a nightmare.
Yeah.
And hopefully, as it starts evening out in those changes in speed, it should start amplifying the amount of vibration that we get. The majority of the tuning time takes place after we have done the initial speed up, the initial charge up, and the Tesla coil set to it. Once you have those three things set, then comes the real long patience-building part of the process, which is tuning the ultrasound piezo buzzer to change its characteristics just enough that it slides into this resonance notch that we've created with these three different interacting components.
Okay.
Once we get that in there, it can kind of make all three of those components all start to line up. The slight differences in the electric field, the magnetic field, and the angular momentum. We can slowly get those three to kind of start coming together with the ultrasound. And the application of that ultrasound, it ties together everything somehow, such that when you pulse that ultrasound after it's tied them all together, it seems to be inverting something in there. It either inverts it or it creates a massive spike where all those resonance modes have overlapped. And it's either that spike or that inversion that allows this thing to actually do the lifting force. Once it's achieved that state, once something is inverted, or once you've done this spike and it's synced everything together, from what we've been able to see from Alexsey's things, it would appear as though that once it's in that state, it's good to go. You can do just about anything you want to it. Alexsey pulls all the power from the thing and it stays in the air for 20 seconds.
Yeah. Yeah, so it's all about building up that state and getting it there. So how long does it take? So you haven't turned your Tesla coil on yet, right?
Correct. So it takes about 5 to 10 minutes to get the discs all sped up. It takes about 10 to 15 minutes to get the rotating discs all charged up. So we're already into it for about 20 to 25 minutes. Then I turn on the Tesla coil. You don't need to wait very long after turning on the Tesla coil. A couple of minutes though, because it is causing differences in that eddy current, because it splits that eddy current, separates out and pushes out that magnetic field, which is going to affect the mechanical resonance state of the spinning discs. So you turn on the Tesla coil, you wait a few minutes for the spinning discs to settle back into a nice steady resonant mode. After you turn on the Tesla coil at about the 25-minute to 30-minute mark, then you can turn on the ultrasound. And then comes the long process of tuning that ultrasound until you see and hear something change. And we are right now about halfway through the high voltage on the discs.
Okay.
The high voltage that I'm applying to the rotating discs, that's coming from a flyback. That flyback transformer is pulsing that DC signal, DC rectified signal, at about 40 kilohertz, 38 to 40 kilohertz.
Okay.
That shows up on the scope, which is one of the ways that I use my equipment here to be able to synchronize the frequency of the ultrasound and the Tesla coil to the applied frequency from the flyback. We are about 2/3 of the way there to having the spinning discs all charged up.
Okay. Yeah, and I'm getting you. As long as you kind of stand in the middle there, if you... Yep.
Some of my more recent tests have suggested that there's contradictions. At times it seems you want as much power as possible. Other times it seems like the more power you put in, the more difficult it'll be to reverse those powers or to synchronize those powers together. So it's not the simple case of just throw as much power at the thing you can until it goes off the ground. No, you need to keep the power levels within this window where it's strong enough to create electrostatic interactions and magnetic interactions, but not so strong that that little piezo buzzer doesn't have the power necessary to be able to synchronize or invert those.
Yeah, so what you're almost describing then is almost like a mechanical form of transistor, right? Or like a mechanical relay.
That's an excellent observation. There is a technology that the radio company Collins came out with back in the 60s called a mechanical filter. And a mechanical filter works like this. You have a bunch of very, very small disc wafers, all equally spaced, and you have some electric leads between every other one.
Okay.
And as those mechanical discs physically vibrate at a set frequency, just like a tuning fork, it's a set frequency, it means that you can use the mechanical vibration of those little discs to notch into a specific RF frequency. So if those discs are tuned or sized just so that you are vibrating at a megahertz, that means that little mechanical filter will filter out everything below or above the vibrational frequency those little discs are vibrating at, which is amplifying the 1 megahertz RF that's coming in and going out. There's some physical characteristic overlaps between those mechanical filters from the 60s and what's happening here, because here it's a similar thing. We have discs of a specific diameter and thickness. We have a physical vibration being applied to those discs, and then we have an RF signal that is being passed through those vibrating discs of a specific size. So some of the first observations that people working on this made was how similar it is to already known existing radio technology, where you're able to filter out frequencies that are too high or too low, or you can even, in some cases, use those mechanical filters from the 60s. You can use those to take a lower frequency radio signal that has higher harmonics. So if I only have a 500 kilohertz, a 0.5 megahertz signal, I can use the second harmonic of that, which is 1 megahertz, for that 1 megahertz radio filter. So even though my input signal is not high enough to work with that filter, it produces higher harmonics that are within the range of that filter. It would seem as though the Graviflyer is operating on similar principles, where we have frequencies all across the spectrum from 20 hertz for the speed of the discs up to the Tesla coils producing harmonics up into the 10, 20, 50 megahertz range. But the physical vibration, the diameter, the thickness of these 3 discs seems to constrain where the actual sweet spot is for the mechanical filter that is the Graviflyer. We are about 80% of the way there to being done charging these up.
Now, does having this cord touch the... Will that change it?
It changes the vibration a little bit.
Does it? Yeah.
But...
Is that how Alexey does it?
Alexey actually runs all of his wires. He drills a hole in that center disc, and he runs all of his wires through a hole in the disc.
Okay.
I don't do that because when you run the RF from the Tesla coil through that disc,
it arcs the disc.
It ends up interfering with all those other signals. Now, I know it works for Alexey, but some of the characteristics of Alexey's design are very, I don't want to say dangerous, but it leads to arcing and destroying of a lot of the different electric components that you're dealing with. And I would much rather do something slightly different that is hopefully not going to affect anything in order to protect my equipment so that I can keep testing, rather than follow his design to a T, which would result in many dollars lost, much time lost by burning out all my equipment. Which is what I did in the beginning of all of this testing, was I burned out my equipment because I followed his stuff a little too closely. Alright. We're about 90% of the way there.
Yeah, and so you don't have the Tesla coil on yet.
Not yet. So I have one more adjustment to make to the high voltage. Wait a minute or two after I've made that adjustment, and then I can turn on the Tesla coil.
Now, I think I hear it speeding up a little bit.
I can see from my lab view that's connected to the oscilloscope that is taking measurements from the speed of the discs. I can see any changes in speed on here. Right now, it does not appear as though anything is sped up or slowed down significantly.
Okay.
If anything, by applying this high voltage to the spinning discs, the top disc should start slowing down over time.
Okay, okay.
Which right now, the speeds of our discs, the bottom disc is spinning at about 1940 RPMs. The top disc is spinning at about 2360 RPMs. So in Alexey's device, he said that the bottom disc was spinning somewhere in the range of 2,000 RPMs, and the top disc was spinning somewhere in the range of 2,500 RPMs.
Okay.
And then another time he said it was 2,500 and 3,000. So his numbers changed some because he's not actually measuring the speed of the disks. He has measured the speed of the disks, but the tool that he uses is very noisy. I have the same tool. It's very noisy, so sometimes it doubles the speed on there. But either way, it suggests that you want to have a couple hundred RPM difference in speed between the top and bottom. The reason for that is probably because the top disk doesn't have magnets on it. So for it to interact with that eddy current in the center disk, it needs to spin faster. Alright, I am now making my last adjustments to high voltage. Okay. Make sure you stay far away because it may arc. Now, if you move your head at different heights around the craft, you'll hear different sounds.
Yeah.
There's a slight, a higher pitch vibrational sound than this lower pitch that we hear. That higher pitch is coming from the vibration of the spinning discs. The lower pitch you're hearing is coming from the vibration of the center disc. It may also be that special sound Alexey describes is coming from changes in the vibration of the spinning discs. Alright, I think I'm ready to turn on the Tesla coil now.
Okay.
Now, unfortunately, when I turn on the Tesla coil, I lose all semblance of measurement for the speeds of the discs. The RF overpowers all of the small wires that are going to my optical sensors measuring the speeds. So we won't be able to see how that affects the speeds. We'll only be able to listen for changes.
Yeah, and again, you want to be back a little bit closer this way.
Right now, our Tesla coil is ringing beautifully. It is in a Slayer exciter circuit mode, which means that it's a self-resonant circuit. If you make a slight change to anything on here, the Tesla coil is going to respond accordingly and automatically retune itself so that it's resonating with those changes.
Okay.
It's one of the simplest designs for a Tesla coil that you can do. It's the design that Alexey used, and it just so happens that that self-resonant, self-tuning type of circuit that he's using would appear to be optimal for this system that has so many non-linearities to it that if you were to try to tune the thing manually with all the different changes, you would never in a million years be able to match that Tesla coil to this. Now, it's very important for the next steps that we do not move closer or farther away from the Tesla coil, or I mean to the Graviflyer. The reason for that is because as you bring your body closer or farther away from a Tesla coil, or the top load of the Tesla coil, which is the center disk, as you bring yourself closer or farther away, you change the capacitance of the system, which changes the frequency of the system, which changes the power output of the system, which changes the response of all other associated parts. Now I can already feel the RF in the form of just a little headache that starts. And the farther away you are located from the thing, the longer it'll take for that headache to start. But since I'm standing pretty darn close to it, even though it won't show up on camera, I'll still attempt it. If you bring this bulb close, it will light up. And this bulb is a fluorescent bulb that is indicative of just how strong that electric field coming off of it is. That's about the right setting for the test coil. Now I'm going to start the very long process of tuning the ultrasound.
Okay, so now we're moving the ultrasound in. We're turning that on, and that's...
All right, ultrasound on.
Okay.
Now you can hear that.
Yeah.
It's a high-pitched squeal. That's the lowest frequency that you can get with this particular setup, and it's somewhere in the ballpark of about 5 or 6 kilohertz. As I increase that frequency, we may see some slight changes, or we may hear some slight changes. Now you can get that piezo into the most annoying sound possible, where it's really screaming. Right there, any changes, because it's operating on the very edge of its resonance mode right there, any changes to the fields around it are going to kick it into a different mode. When you make an adjustment to the ultrasound, there's about a 10-second delay, 3 to 10-second delay between when the electric characteristics of that piezo start matching the system, or vice versa, the system starts matching those characteristics. That interaction delay time I have observed with my scopes in the RF regime. So even though this piezo right now is operating at 7 or 8 kilohertz, we can see changes up in the 14 to 20 megahertz range, those high harmonics of the Tesla coil, because right now there's an electrical connection, an air-gapped electrical connection between the Tesla coil being applied to the center disc and the ultrasound buzzer that's located about 5 inches away from that center disc. It's like you're holding that ultrasound buzzer up really close to a radio antenna.
Okay.
It's going to act as a receiver, and if you have a signal being applied to that thing, it'll act as a modulator to the entire Tesla coil radio frequency system. It's also possible the special sound Alexey describes could be the ultrasound buzzer itself. When you get the ultrasound buzzer into a specific state after you get into the ultrasonic regime, it has higher and lower harmonics. Well, when it's up in the, let's say, 40 kilohertz regime, very close to the frequency being applied from the high voltage static flyback, the piezo has a lower audible harmonic around the 9 to 12 kilohertz range. Oh, shucks. So right there,
that was an EMP?
Right there, my high voltage, I had set my high voltage to about just a little bit more than I normally do.
Okay.
Just a little more, because I was hoping to make for more noticeable effects. Unfortunately, that was just enough that when I had the ultrasound set to a specific frequency, it caused the surface charges on those discs to be vibrating, which was increasing the overall strength of that electric field, which allowed for arcing. Now, thankfully, I turned it all off pretty quick with only a few arcs, so hopefully I didn't burn out any of my equipment.
Is there a way that we could turn them back? I mean, like, is there a way that we could restart this without having to go through the whole cycle process?
Nope. You have to start from step one.
Okay. Well, and the reason I ask is so I'm getting a hot card on the memory, so it's just.
We'll probably have to turn it off and let that cool down along with the Graviflyer. It needs time to cool down, which is really just allowing the trapped charges in the rotating disks time to come out.
Okay.
Because I think the polarity of those trapped charges is very important. And as you turn everything off, the polarity is now not as uniform as it was, which is why you have to let it discharge.
Let me do this. I'm going to stop recording then. Yeah, there we go. Okay, go for it, man.
All right, so using the magnetic field meter, I can show not just the magnetic field strength, but its polarity as well. So when I put this probe right over the eddy current that's being put into the center disk from the spinning bottom disk, I can see it's like, you know, ballpark 5 Gauss at these speeds and distances, and that it's the south polarity. But if I scooch that in closer and closer towards the center, now it's a north polarity at 5 Gauss in the dead center, right? So we're creating like an eddy current donut where you have the north field is facing up this way in the very center and this way at the very outside edge where the eddy current ring is.
Okay.
So you're creating like this cone-shaped, you know, sombrero hat-shaped magnetic well with the spinning disks. And then if we measure the polarity on top of the outer edge of the second disk, the top disk, this counter-rotating, we can see that I get about 2 Gauss, and it's a south polarity as well, right? So the direction of this magnetic field, it starts at the bottom spinning disk, and it just keeps propagating its way up, 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 all the way into this top disk. And you can see there's an eddy current in this top disk. If I come here all the way to the outside, so I have south on the center of this top spinning disk, and I have south on the outer edge of the spinning disk. The whole spinning disk has one polarity, but the eddy current in the center disk has 2 polarities. So it's south on the outside and north on the inside, but the spinning disk is south on the outside, south on the inside. So when you look down at the edge-on view of this disk, especially with a larger disk, it's a little more apparent, but the very center of this disk is pulsing up and down like a drum head. And the point at where that pulse is occurring, the node for that pulse, is right about where the eddy current ring on the outer edge is located. There's different magnetic field strengths, because if the disks aren't perfectly parallel, you're going to have magnets closer on one side and farther on the other side, so the strength of that eddy current is going to be unbalanced. So what I need to do is I'm going through and I'm balancing it with my Gauss probe here, which helps me kind of make small adjustments to the height of these 3 arms so that I can get that eddy current ring to be as equal in strength all the way around as possible. My suspicion is that in the videos where Alexsey gets his craft to tip over, the reason why it's tipping over is because that eddy ring magnetic field strength is not uniform. He's got one that's just a couple of turns different on one of the rods, and so it's a little off-can or a little off-parallel. So it results in not a uniform lifting force. So, since I haven't gotten as far enough to lift yet, I gotta do everything I can to try to give myself the best chances possible, which means balance these magnetic field strength forces by small adjustments in height.
Yeah, this is very interesting because there is such a complex interaction at play here. One of the things that I saw last night was even this 300 milliwatt piezoelectric transducer you were using makes a massive difference in rotor speed. And when you think about you know, the rotating mass that's involved, as well as the size and power of the electric motors, to have anything at 300 milliwatts even influence that is amazing.
Especially since it's so far away from everything, and it's at ultrasonic frequencies, which are significantly attenuated and dampened as they go through air. So by the time that ultrasound signal getting pumped at 300 milliwatts gets down to these plates, you're talking less than 1% of that energy is actually making its way to these discs. Arg. I think instead of adjusting that up, I'm going to adjust it way down. Way down.
And so the change that we're hearing here is just from the inductance, right? That's
correct.
But again, all of these elements have this complex interplay, so changing one of them tends to influence the rest.
So right now, between my strongest of the three positions and my weakest of the three positions, there's about a 50% difference in magnetic field strength of the eddy current. And I'm trying to get that down to within a 20% difference or less. Which I'm getting closer. I'm getting closer. That's looking a lot better. Alright, we're at 6.4 there. We're at 8.2 there. We're at 6.5 there. So if I lower this other corner here, I should be getting much closer in the ballpark. Which, I mean, it might even be noticeable on camera how off parallel this is.
Yeah, I'm at an angle so I can't see it.
But I don't care about parallelism of the discs. I care about equal magnetic field strength. Okay, so now we're at 7.6 for our strongest one. And 6.5 for our weakest. That's getting pretty daggum close.
Okay, so I'm recording with that one.
Okay. Now I'm going to go through the slow process of applying the high voltage. So,
and then with this one, let me see. Put this on video, 4K. Okay, so we're recording here. Do you want to set this one up so that it can kind of get me?
There we go. Yeah.
Okay, so yeah, I think we're all pretty much all set.
So when I balance the magnetic field like that, and I get the speeds pretty well balanced as well, I'm bringing the two rotors into greater interaction with each other, which means that the speed of one starts affecting the speed of the other more. And when you have a somewhat balanced field strength on top and bottom, that means that you can get them into a situation where the speeds of the two match up. At the moment when that happens, if everything falls into place, the speeds of both will either increase rapidly or decrease rapidly.
Okay. Well, if it's okay, let me back up.
All right.
Okay. Make sure I don't have any mic noise or anything like that. So this is like the 6th run that we've done with this. You know, we've been working on this for several days. We've seen a bunch of really interesting effects. The thing that I would point out is this is an incredibly complex relationship. It's a system that has a number of different parts. You've got 2 different kinds of high voltage going. You've also got inductance, you have mechanical spin, and you have a piezoelectric transducer. And some of the really interesting things that I've seen are, for instance, that piezoelectric transducer is only 300 milliwatts. It is absolutely tiny, and yet it influences the speed of those motors. So there's a lot going on here, and changing one piece definitely affects the others.
Absolutely. That little piezo buzzer, when it's at its lowest frequency, it has the highest amplitude output, which is around 3 to 4 watts. And as you increase the frequency of it, the way the circuit is designed, it starts putting out less and less power. So by the time you're at the highest frequencies it puts out, around 40 to 45 kilohertz, the amplitude going to that piezo has dropped by a factor of 10.
Yeah.
Additionally, air itself is not a great conductor of sound once you get into the ultrasonic regime. That's why we evolved to be able to hear in the frequencies that we can, because it's really efficient for the power of the sound wave to get to your ear. So that means that of the 10% power that it's now applied at those high frequencies, only 1% of that is actually making its way to those discs, and yet it still's enough that when all factors are included, it can affect the speed and the vibration of those spinning discs.
So the other thing that impressed me was, again, the quality and diligence of your work. On the mechanical device, you're basically taking Alexey Chekurkov's original design and kind of iterating on it, you know. But in terms of measurements, you have a very thorough and precise system in place, and it's exciting to be able to see these waveforms where you're tracking all these individual elements. And then again, you've put all of that into a spreadsheet as well, which is absolutely massive. And so what you're trying to do is basically tease apart this claimed effect that he's talking about.
Exactly. The things that I'm measuring with my equipment are the speeds of the rotors, which when I connect it with LabVIEW on my computer, I can see how those speeds change over time whenever I make a slight adjustment to any one of these interacting parameters. I'm observing the RF, the electromagnetic field around the craft, as I introduce the RF from the Tesla coil, or the 40 kilohertz pulse DC from the high voltage flyback to the spinning discs, or even when I apply the ultrasound to the piezo buzzer. That causes a change to the electromagnetic environment around it, and I can pick all of that up with my spectrum analyzer. Additionally, I record all of my tests, so I can go back through all my tests and I can observe my waveforms and that recorded data to be able to see what exactly did I change when I got all of these different fields to line up together, when I got all these subharmonics and higher harmonics to somehow overlap and create a higher amplitude single signal, or conversely, how did I make it so that pushing the button on this ultrasound caused a drop in the third harmonic of the Tesla coil. Weird stuff like that you wouldn't get. Alexsey certainly wasn't able to get it because he didn't have this equipment. You have to be able to observe all the different parameters simultaneously. Otherwise, you're going to miss so much.
So at the moment, right, again, I mean, this is like, I think, probably the 6th run that we've done. While I've been here, you have done hundreds on your own. You haven't definitively seen lift or anti-gravity or propulsion or anything along those lines, right, that you can truly identify. But what you have seen are a collection of really interesting electrical and systems effects that Alexey predicted. And I think that is worth pointing out, is he's kind of taking you down the rabbit hole in terms of when you change this, you should see this. And every time you follow those instructions, that's what happens.
That's exactly right. Alexey has given us a host of different parameters to follow, as well as mile markers along the path towards lift that you should see. And some of those things include these EMP events, where we've observed it over live Zoom calls with Alexey. When he gets the craft to lift, at the moment it does that, it releases a giant pulse of energy that it knocks out his computer, his cell phone, his router. It even knocked out his space heater, which, for anybody who understands electronics, space heaters are pretty well protected against a big EMP pulse. And yet, his was powerful enough with a bunch of little 12-volt power supplies to be able to knock out a 1,500-watt space heater. I am almost done with one of the steps along the path, which is applying high voltage at slowly increasing amounts to these spinning discs.
Okay. Well, I'm going to turn on the 360 cam. Okay, there we go. Well, Jarod, let me thank you for bringing me in to see this and try and film this. And
it's been a real treat. You have brought a lot of great ideas along with you. I have been meaning to get this balance arm set up going for a while, and you finally gave me the good kick in the butt, and we set it up last night. And now we have hopefully somewhere in the range of 100 to 200 grams worth of measurement capability of lift, which we probably won't see that today, but who knows? It is better than the setup I've had up until this point, which only really let me see lift or no lift. Unfortunately, for the longest time, I have this weight scale, this luggage scale that I tried over and over to be able to use. Unfortunately, because it contains electronic equipment inside it, it means that it starts freaking out as soon as I turn on all of these strong electric fields, and it no longer is able to measure the weight. So it's only really good to let me know the initial weight of the craft. And then another thing that I used for a while are these force gauges, which these things are measuring in newtons, which newtons are kilograms, I don't really care which. The problem with these is they have internal friction. So these things were good to test to 40 milligrams of sensitivity. Unfortunately, since you have vibration from this craft, vibration causes this thing to stick a little bit on the sides and create dust on the sides. So that 40 milligram sensitivity, or 40 gram sensitivity ends up turning into something like 100 or 200, which is not enough.
It looks like it's smoothed out. Should we try and turn on the Tesla coil here?
It has. I need to get the voltage a bit higher yet. I'm almost there. I should only need about one more adjustment. Alexey instructed us to get the electric field as strong as you possibly can without arcing. So he's running the electric field strength to these spinning discs at maximum possible voltages, right below the threshold of arcing.
Yeah, and again, just to kind of remind everybody, so yourself, Charlie, Mike Gamble, and then David Chester is providing some consulting assistance on this project. Nathan Bunton is involved, although a little bit less so. So Charlie was the one who started this all out. Charles Crawford. We got to give Charlie a big hand because this was his. He got bit by the bug. This was his baby. He's put a ton of Alexey's videos online and compiled them. And he is actually working with one of Alexey's devices. And so he is trying to basically follow the instructions precisely. In your case, you're trying to kind of iterate on that and see how changing things may affect it.
That's right. So I've tried making larger Graviflyers and smaller Graviflyers. I've tried adding more magnets or fewer magnets, magnets on both top and bottom, like Alexey's first designs. I've tried, instead of using a single piezo, I've tried creating stacks of piezos. I've tried magnets in different arrangements on the discs. I've tried alternating magnetic field strengths along the outer edge. So one of these discs I have with magnets on it, it's got 30 magnets around it instead of 6, and every other magnet is slightly weaker than the one next to it. So it goes in 52, in 42, in 52, and my goal with that was to create a more uniform field that still has a slight variation in it, like you would get with the gaps between, like you normally have. Every single one of these iterations I've done has taught me a little something.
Yeah.
And fortunately or unfortunately, every single time I try to deviate from Alexey's design, I observe certain nuances that make it more difficult to tune. That somehow Alexey, with his many years of iterations on this, he came up with a design that seemed to work really well. And I've yet to find a design that seemed to get as close to lift as the first one that I built, which was as close to his original specifications as possible.
That's intriguing too, because when you look at Alexey, you know, the way that he presents himself, I guess, I mean, again, he's using cobbled together equipment, right? It's just bits and pieces and parts that he's able to find. So it is definitely not like a slick, polished presentation. The shielding that he uses to prevent RF headaches is, you've got like a tinfoil covered motorcycle helmet, right? So it is intriguing to see the difference, I guess, between the way that a lot of people would perceive him versus getting into what he's actually describing. Mm-hmm. And again, just in the couple of days that I've been here, you know, I've seen this myself, where he will have given you advice and said, follow these instructions, and this is what you will see, and if you don't do it like that, this will happen. And I've seen that in play.
That is absolutely the case.
Yeah.
I am now ready to turn on the ultrasound, so you're going to hear the screeching sound, the siren call of my people.
Okay. This may affect our mics too. I'm not sure.
It might. As long as we keep a little bit of distance away from the device, it shouldn't let the RF affect our mics too much. And the screeching sound, hopefully that does not get filtered out, because I think there's value in being able to hear that frequency and let folks analyze it in a sound analyzer. If we see some kind of lift, they'll be able to tell exactly what frequency I was at, if it's still within the audible range.
So one of the things that you shared with me last night was the piezoelectric transducer is actually outputting more power at these lower frequencies. When you get up to the higher ranges, that's when it goes from a couple of watts down to milliwatts, right?
Correct. So at this frequency you can hear right now, we are using 4.6 watts, 4,600 milliwatts. As I get to the highest frequency possible of around 45 kilohertz, That's going to drop down to about 270 milliwatts.
Okay. And yet it will affect those motors. Those are pretty heavy-duty motors, and they are constrained partly by induction, right, which is creating this eddy current, as well as the power that's going into them. So again, they have a lot of energy going into them, and they're somewhat locked into their own rate. That tiny little piezo transducer is absolutely affecting the speed and the resonance.
Correct. So little piezoelectric buzzers, a lot of people think of them as either a speaker or a microphone. Those little piezos are also used in microphones. They're called electrets, which is an electrically polarized, permanently polarized little piece of crystal. Well, in this case, that electret, that piezoelectric buzzer, has many electrical characteristics about it that means that it is acting as a little antenna for the signal that we are sending to it. So this whole device, you're mixing multiple signals. It's called heterodyning. You're heterodyning multiple signals. You have one signal, which is a very low frequency signal, the spinning of the disc with the magnets, and right now we're at about 30 hertz, very low frequency. Then going above that, you have the ultrasonic frequency, which is in the tens of kilohertz. In that same similar vein is the frequency of the high voltage being applied to the spinning discs, which is about 38 to 40 kilohertz. And then you have the Tesla coil, and the Tesla coil is operating in the hundreds of kilohertz and megahertz range. You have a 360 and a 720 kilohertz signals, subharmonics, and then you have a fundamental frequency of about 1.4 megahertz off of that Tesla coil. So you're taking these very low frequency signals and very high frequency signals, and you're using all the harmonics of those signals where they have overlap happening in order to increase the amplitude of those enough that you're able to affect different components within the device. So the ultrasound at its tens of kilohertz is affecting the output of the Tesla coil in the megahertz range. You're coupling together all of these different frequencies of fields into a single unified field that is changing very powerfully.
So the ultrasound is right on the edge of being audible.
Oh, there it was. Got an EMP. Yep, there it is.
Okay, there we go. Here, I'll shut all the cameras and stuff down. And now we're recording here.
All right.
And I can hear us fine.
Check, check.
Okay, and there's definitely background noise, so.
Yep.
Okay, so that's running.
And walk very slowly by the water jug. That was still too fast.
There we go.
Very slowly. Perfect. All right, so the speeds of both discs is pretty darn close right now. They're within about 15 RPMs of each other. We've had these discs spinning for about 10 minutes now. And the speed of the top disc is still slowly oscillating faster and slower. But when I first turned it on and first started it up, it's set so that the top disc is spinning about 350 RPMs faster than the bottom. So as this eddy current in the center disk gets built up in strength, the two spinning disks, their magnetic fields start to sync up because of that eddy current, and that ends up pulling down the speed of the top disk so that they're matched more.
Okay, and so I should mention this is like our 7th run now. In the last one we had an EMP that knocked out the motor controller, and so we're just kind of restarting. We'll see if we can make this thing work.
Fingers crossed. All right, I got to give it another few seconds here. I don't want to turn on the voltage until the speeds are fairly even. The top disk is slowed down a bit, so
yeah.
Give it
so one thing I should mention, again, for anybody who watches this is, like, people are going to watch this and come up with ideas. Why don't you change this? Why don't you change that? One of the things that I've seen is it's precisely calibrated, right? You're adjusting little components that I hadn't even thought of to get this eddy current where you want it. So part of it is that. The other part is you have tried over the last several months thousands of variations on this, and so I spent over an hour suggesting ideas the other day, and you were like, tried it. Yeah.
So one of the more common suggestions people have is people have heard about T.T. Brown. He's kind of in vogue again. So people suggest that this thing is kind of acting like asymmetric capacitors and the lifters that T.T. Brown did. So somebody suggested a long time ago that I should try that, and I did.
Okay.
I ended up replacing the center disk with HDPE, which is a really thick plastic that's got a good dielectric constant, so it's an insulator. And then for the bottom disk, with the magnets, I made a very small bottom disk and a very large top disk. And they are, I made it out of musical cymbals, like these musical cymbals here that you see on drum sets, because in the T.T. Brown thing, it's a curve, right? So I had the curve, I had the two different sizes, and I ran the voltages up to the maximum that this flyback could produce, which is about 35 kV. One of the issues with trying to say that this is acting like T.T. Brown is the voltages he was dealing with, he wouldn't see any thrust until about 50 kV.
Okay.
And then where you start talking about getting kilograms of thrust necessary to lift this thing up, T.T. Brown didn't get that kind of thrust until 100 to 150 kV.
And you probably want to scoot forward a little bit.
Oh, there we go.
Yeah, because your chair rolled back, yeah.
So I've tried the T.T. Brown angle, and it didn't work, and it makes sense that it didn't work because T.T. Brown used voltages that were so much higher, an order of magnitude higher than Alexsey ever used.
Yeah. Yeah, that's one of the things that you pointed out to me, is that in your assessment, this is not about raw power. It's more about tuning, and that raw power actually prevents it from doing what it needs to internally synchronize, I guess. So. And
another thing that people have tried to suggest for the mechanism of lift is people are saying that it's an ion thruster. The problem with that is when you look at a $100 million satellite up in space right now that has a lot of engineering effort behind it, the amount of thrust they're getting from that $100 million thruster is a fraction of what this junkyard-built, garage-built thruster is getting.
Well, I think there are things that we could rule out. Some folks have suggested that this is some kind of an ultrasonic levitation against the Earth. I would say that's absolutely implausible. I don't see any possible way that could happen. The ultrasonics being used are minute. They do affect the components in play, but they're not having a major effect on the outside environment. The other thing is, in terms of airflow, there's a tiny breeze flowing, less than a fan. So, you know.
Here's the little piece of tinfoil, right? And you can see how little that tinfoil is blowing around.
This is not, it is not an aerodynamic vehicle or effect of any kind. I think that we can safely rule those out. So whatever Alexsey appears to be demonstrating in his videos, it's not conventional, that's for sure.
Very unconventional. For the ultrasonic lifter, this little 27mm buzzer that costs $1 is what Alexsey was using. And this thing has a maximum power output of about 5 watts. And when you look at trying to lift 1.5 kilograms up to 5 meters off the ground is the highest Alexey ever got it, with a little 5-watt piezo buzzer. It doesn't take all that much thought to realize that that's just not plausible.
So I guess thinking about his videos, some things that do make more sense now are why the device is going to keep itself like somewhat stabilized. The power cords definitely play a factor in that. You have a fair amount of cord weight there. And the higher that gets up, the more those cords are going to be lifted off the ground, so the more cord weight you're going to be carrying. So, you know, for people who are like, how come it stays stable? I wondered that. How come this thing tends to remain stable in the air? And how come it goes up to a certain height and stops? I could attribute that easily to just cord weight.
Absolutely. There was a very recent, somewhat recent, within the last year and a half video that Alexey gave us where he was testing outside, and he was testing in a field that had some tall grass, but there was a lot of sticks in the field.
Yeah.
And so you can see the Graviflyer, as it lifts off the ground, it gets to about 2 feet off the ground and it kind of gets stuck, and it wants to go farther, and so it's testing, and it's very windy, so it's kind of blowing a little bit in the wind, and then finally after a few minutes Alexey goes over there and he like pulls the sticks off of those cords, and now vroom, he gets the extra foot or two of height.
Yeah.
Because the cords are absolutely doing it. And then in order for him to get it to go higher and higher, he's adjusting the ultrasound and the Tesla coil simultaneously. He turns the frequency of the ultrasound up and turns the amplitude of the Tesla coil down just a little bit. When he's doing that, you can see the entire Graviflyer, it goes up in discrete increments. It doesn't go up smoothly. It goes from one height to another height. And there's a couple of his videos where you can see this happen. I went through pixel by pixel and analyzed it. And it turns out it goes up in increments of 1.5 rod lengths, vertical rod lengths, which is equivalent to the diameter of the center disk.
Okay.
Which is a very interesting feature to observe, because if this thing goes in discrete amounts and those amounts just so happen to correspond to a dimension of the device itself, that's very telling that that dimension of the craft is probably pretty important for determining how it lifts.
Yeah. Yeah, there are definitely a lot of factors involved with this. I've seen that just over the last 3 days. And again, going back to Alexey's videos, I've looked at those very, very closely. I used to have a 4K one that I went through, and they, to me, I mean, to the naked eye, it doesn't look like how it could be real. I did not see any way, I was like, how could this be faked? But you know, with all the demonstrations, the many videos that he's done, him waving sticks, his arm, his hands, all of those things, you know, it doesn't appear to be a hoax, at least in any way I can envision. And those videos haven't been CGI edited, so. If
there was only 1 or 2 videos, then the argument that it was all faked is very strong.
Yeah.
But Alexey's released over 20 different videos of this thing lifting, and he was willing to do it live over Zoom multiple times with my team.
That's true.
And if you're a scam artist, you're not going to do the same trick in front of the same people more than once, and you're definitely not going to do it live where, you know, there's a chance that they're going to be able to uncover the trick. And then just for a third fact, we've got 2 of the devices he has built. One of the devices that's the most famous one in all of his videos, we have that one, and then we have another one that he built for us. So if you're a scam artist, you're not going to give people the original from the scam. That's a great way to have people uncover the scam too. So just time and time and time again, there's these little things that suggest he is most certainly not scamming us.
Yeah, this is one of those mysterious devices.
So right now I'm slowly increasing the high voltage to the spinning discs. You got to do it slow if you do it very fast, the voltage on the discs does not end up reaching as high of a level as if you do it slow. This was a piece of instruction that Alexey gave us recently that we didn't know, was that you have to apply this slowly over time rather than just all at once. Otherwise, you're not going to get the effect.
Okay.
But you can't do it too slowly either, because if you do it too slowly, the ozone builds up around the craft, and that can cause arcing, which is similar to the EMP that we just recently experienced.
Yeah.
That's because I took too long to adjust the voltage. So there's a window of time that you have.
Well, hopefully we won't have an arc in this test, but again, I think the value that we're providing by filming this, and again, thank you so much for having me over to do that, is we're helping to give people a little bit more details about how it's constructed and how it works. And my hope is to share like the vision that you have been chasing for like a couple of years, over a year now. And again, Charlie has been into this for quite a while, right? So
Charlie started about a year before I did, and he managed to get a hold of the original craft and reverse engineer it and put out a parts list recipe for anybody who wanted to replicate it. And as soon as he did that, I jumped on board the Graviflyer boat and been dedicated to it ever since. I've probably put somewhere around 2,500 to 3,000 hours into this project.
yeah. Lots and lots of hard work, and it shows the amount of, like, just in terms of the measurement and calculations and data that you're collecting on this. You know, it's amazing, it's high quality, and it shows how much you put into it.
We're about 2/3 of the way there with the high voltage. I'm going to start speeding up a little bit faster on how quickly I get it to that max voltage because, like I said, I don't want it to arc.
So you have the high voltage DC turned on then?
Right now, the only two parts of this that are going is the discs are spinning and the high voltage DC from the flyback is being applied.
Okay.
And I start at about 10 kilovolts out from the flyback, and I end at about 20 kilovolts out. And that's getting split into positive and negative components, with the positive 10 kV being applied to the top disc, and the negative 10 kV being applied to the bottom disc. And because we have magnets on the bottom disc, which are pointed north upwards towards the center, and it's going counterclockwise as viewed from above, you're following the right-hand rule so that you're maximizing this. Same goes for the top disc. Because the eddy current from the center disc is getting transferred to that top disc has an eddy current, which is north up on the top, it's south down, and it's positively charged, and it's rotating clockwise as viewed from above. So you're following these right-hand rules in order to maximize the strength of the magnetic field by rotating these charges in the direction they want to rotate in the magnetic fields that they want to be rotated in. Which is yet another thing that Alexey got right. He got the right-hand rule correct, which if it was a scam, he might have also gotten that right, but it's just one more little notch. All right, and I'm gonna end at a slightly lower high voltage than last time when we got the EMP. So instead of 20 kilovolts, I'm gonna be at closer to 19 kilovolts.
Okay. So I think after that, we turn the Tesla coil on, right?
Next step is the Tesla coil.
Yeah.
So once I reach this maximum voltage, we need to wait a minute for the speeds of the discs to acclimate, because the discs are magnetically coupled together through that eddy current. So there we go. I've now reached maximum voltage. And now I'm just listening for changes in the speeds of the discs, as well as watching the power going to the motors of the discs to see if all of a sudden the power draw changes.
Did the camera stop? Oh. Got it. Oh, it was that one.
Oh.
Yeah.
Slow, careful.
Yeah, because it ran too long.
It's okay. Very slow, very careful.
So we're learning the limits of our Insta360 camera too.
You can only stay on for about 30 minutes before it starts.
Yeah, so it's good for short activities. In fact, why don't I carefully check on this one?
Okay, we're looking good?
Yeah.
Okay. Slow. Time. Okay. I think I'm ready to turn on, test the coil. Getting some nice arcing on that brush.
And what I am going to do is put this camera up and
go. And 3 is going away. All right, so right now on my oscilloscope, I'm watching two signals. I'm watching the signal from my flyback, which is operating at 40 kilohertz. And I'm watching the signal that is being received from the piezo. So the electric field is around that piezo. The piezo is acting as a receiving antenna. And I'm measuring that through the output wires that are going to it. And in this way, I'm able to observe how these pulses from the beat frequency and the eddy current interact with these much higher frequency DC pulses coming out of the flyback. So essentially, this is measuring the DC pulses of the flyback as felt by the piezo. Now I think I'm ready to turn on the piezo. Now I don't think I've changed the frequency on this from where it was at when we got the pulse. So let's see what happens. Oh, I guess I did, because we're way down at the bottom of the frequency. That's okay, we're gonna get back up there.
Okay. Do you think I could ask you to set that one back down to... Thank you, sir. So you're slowly increasing the frequency and then you're listening for a change in the overall system.
That's
right?
correct. As I increase the frequency on the ultrasound, on the piezo, the output power to it goes down. So once I get above the audible range, in order to really know that I'm still increasing the frequency, I have two methods. One, I use software on my computer along with my microphone that can measure up to 25 kilohertz. And that helps me hear above that 17 kilohertz range where your hearing stops. And the other way is I have the power supply to this draws less and less power as you get into those ultrasonic frequencies. And so I can just watch until I get to the minimum power, meaning I'm at the maximum frequency. There should be a few spots where it'll become quite noticeable. We'll hear and see some vibrations in the center disc. We might end up just getting an EMP. You might hear the speeds of the spinning discs change. Is the very slow process of sweeping through these ultrasonic frequencies until you can get to the proper point. Now, I've done many hours of these sweeps, and I used a signal generator for the first year and a half.
Okay.
Because it's much more precise. You can choose exactly where you want to start and stop your sweeps. And I've been able to get some successes with that. I've been able to affect the power output of the Tesla coil using that signal generator going to the buzzer. I've been able to affect the speeds of the spinning discs using the signal generator, but I've started trying to replicate a few more items of Alexey's original design as it becomes more and more apparent that there's a method to his madness. And one of those designs that you cannot replicate in the signal generator is the very last step he does, which is press this signal interrupt switch.
Okay.
Because there's a transformer inside this thing that when you press that switch, there's a very brief pulse of energy that goes to that piezo. And you cannot do that with your signal generator. Your signal generator doesn't have that kind of capability to send out a certain sine wave signal and then pulse that signal as it turns it off.
So it's really about getting the piezo to the correct frequency. And again, this is like a mosquito moving a mountain because you've got so much mass and energy stored in this system mechanically. To have something at like 300 milliwatts have any effect at all on that is remarkable, you know. But yet it seems to. So you tune this in, and from what I understand, really you're pushing a button. It's an interrupt button, so it disconnects the ultrasound, but there's also a pulse of energy before it does that. Presumably that is enough to change the eddy current, and hopefully someday we'll see lift.
That's exactly right. Pushing the button is kind of like breaking the dam. The stored energy in the transformer in here just immediately gets dumped, but then there's no more energy to dump. There's no more water in the reservoir. And so the piezo just stops until you let go of the button. You rebuild the dam very quickly, and the energy gets stored up again. So Alexey, when he gets it to lift, he's pushing the button,
For about 200 to 400 milliseconds, he'll hold the button down, which is more than long enough, and he'll press it about 3 to 5 times. And he presses it with very long intervals in between presses that slowly increases in speed. So he'll press it, he'll wait 5 seconds, he'll press it, he'll wait 4 seconds, he'll press it, he'll wait 3, press it, and then for the very last step, he'll press it and hold it for a few seconds. And then it's either going to lift or it's not going to lift at that point. And he says that he's trying to catch the moment, which that moment he's talking about has to do with, as you're pushing this button and you're dumping this energy from the transformer, you're building up this field where you already have all of these signals overlapping. And then by pressing it and holding it that last time, you're hoping that you have phase locked all of these signals together. And if you've missed the moment, as he calls it, then those signals haven't phase locked. And additionally, pressing the button causes a transfer in charge off of these charged spinning disks. So if you miss it, you have to turn everything off and you have to start again from scratch. Now, I don't know if our mics are going to pick it up, but there's a very quiet hum. See if I can get my microphone close to it. I don't know if it picked it up. It probably didn't because it's very quiet. But that hum is like you're drawing a bow from a violin across a violin string. That is the sound of the metal disc vibrating at a very high rate.
Okay.
Which, since there's a lot of charge on the surface of that disc, the faster that disc vibrates, the charges on the surface, the stronger the field is going to become. Sal Pais describes this as rapid acceleration transients of charges. And his experiment was a spinning conductor, very highly charged, spinning very fast, and then a buzzer, a transducer, that is vibrating 1,000,000 times a second as opposed to 20,000 times a second. And so he's vibrating the surface charges so fast that those charges are having to get up to one spot and they get pulled and accelerated the other way, and they're being constantly accelerated up and down. And according to him, all the secret sauce for his patents lies in that original experiment of spinning charged thing vibrating really fast.
Okay, and one of the things that we talked about the other day was the potential for this to be similar to James Woodward's Mach effect thruster, right? And Woodward, as well as Curtis Horn and Hal Fern, have come to the APEC conference pretty frequently. So it's interesting to see this convergence between different, I guess, approaches. And in this case, maybe this is some kind of a Mach's principle complex mechanical effect, right? Involving vibration or something. That's something that you have to hopefully determine later, you know, once you can kind of get a repeatable lift mechanism in place.
One of the major differences, and I've spoken with their team at length about this, one of the major differences between the Graviflyer and their device is that their device is it's not got a big electric field that they're subjecting it to. It doesn't have a big magnetic field that they're subjecting it to. And so they're using only moving masses.
Yeah.
Whereas this is using moving masses and a bunch of other fields too. So we've talked about perhaps one day down the road, they might try to incorporate a field effect in combination with their device. For now, though, I think they're still just focusing on moving masses, which they've gotten positive results with their moving masses, which, if you already got evidence of something that works and you're doing something along the same vein, who knows?
Now, how long do you think it'll be before you're able to push the button?
Right now, I am about 30% of the way to maximum frequency. Okay. Maybe 40%. So I like to get all the way up to max frequency because it's pretty close to max frequency where we see the strongest effects.
Okay.
Which we should start seeing effects here in about, at the rate I'm going, 4 minutes or so. And you can't go too fast on this step.
Yeah.
Because every time you adjust, you need to wait for that adjustment to take effect with this very non-linear chaotic system.
One of the things that I like about what you're doing and the team collaboration is the openness and the integrity that you guys are doing it with, right? I think especially in this area with so many videos on the internet that claim to purport this, that, and the other thing, you guys have taken something that just has grabbed you and intrigued you, and you're trying to do it in a very open way and an honest way, right? So, you know, the downside to that is it's not going to lift up in all of these videos, but it only needs to lift up once because the integrity that you guys are doing it with is evidence that, you know, if something happens, it's something real.
If our team was going to fake success, we would have done it thousands of hours ago.
Well, this is part of the journey, and there are so many different innovators that have different paths to that, right? Mm-hmm. And so, you know, it becomes the exploration of flight without wings, I guess, flight without rockets, and I think that's the intriguing part.
There is a magic to this idea that you can fly using a method different than what the Wright brothers demonstrated more than a century ago. That there might be more than one way to skin this cat.
Yeah.
And that's extremely exciting to think that there might be a whole different branch of aeronautics that we've never been privy to. All right, I think I'm getting fairly close. I'm about 80% of the way there.
Well, and we haven't had an EMP this time. Those do happen. So.
Thankfully, I've kept the voltage just a tiny bit less so that we don't fry all the expensive equipment this time. All right, we're starting to get into effect territory. And the sound that you can hear is a very slow beat frequency from the spinning disc. And it's observable on camera as the whole thing giving just a little wiggle every once in a while.
Okay.
Another comment on Alexsey's videos. You can observe in a few of those videos when he's getting it ready to lift. He never has shown his tuning process in the videos because he thinks it's too boring for people to watch. And having done it enough times, I can agree. It's like watching paint dry. But in his most famous indoor video in his living room, you can see that the entire Graviflyer immediately before it lifts off, it does this little dance where it's rotating clockwise and then counterclockwise. And then he hits the button and the thing comes up off the ground. Well, I've observed that multiple times, which is indicative that this beat frequency that's causing the thing to kind of twist and untwist every once in a while is playing a role. It needs to be in a very specific state of that beat frequency before you hit the button. So right now, that's kind of what I'm looking for, is I'm trying to adjust the ultrasound frequency to the point where it's starting to have the greatest effect on the electric field, which affects that eddy current, which affects that rotation. All right, we got to speed up on the disc. We're about 90% of the way to max frequency, maybe 95%. And I think I'm ready to hit the button.
Okay. So I'll tell you what, I will focus in on the Graviflyer.
Careful not to bump the jug.
Yep, I'm not close to it.
All right. Press, 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 and hold. And I missed the moment.
Missed the moment.
I think I might have one more shot. Oh, I hope you caught that. I just pressed the button a few times and you could see the whole Graviflyer did a little jiggle wiggle, clockwise, counterclockwise. And I'll have to go back and look on camera, but I swear I saw it deflect downwards just a little, very briefly. See if I can do it one more time. press, 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 hold.
Okay. Do you think I could get you to set that one back down again?
Yep.
Well, so there we go. I think that was test number 7.
Yep.
And again, congratulations on the hard work, right? It doesn't happen instantly. But I think the important part is that you guys have taken something and tried to really explore it and document it as thoroughly as possible. That's, for me, that is absolute most exciting part.
Absolutely. It has been an exciting ride so far.
Well, I should thank you for having me out to film this as well. It's truly, it's a pleasure and a true honor to be able to come out and see hands-on in the lab at work. I've seen this on Zoom, but again, there's just such limits, right, to what can be transmitted there, that to actually see this in real life, I've learned so much about the details.
And we've been talking about this thing nonstop for days, and you can tell there's a lot to learn about it that you can't get across in just a 1 or 2 hour conversation.
Yeah.
I'm still trying just one last try here. There is a notch near the top end of the frequency where there's an audible subharmonic.
Okay.
And anytime I can get anything that's audible, I know that I'm following Alexsey's method of only using your eyes and ears.
Well, I do see a tiny bit of wiggle.
Get a tiny bit of wiggle every once in a while, I believe, because pressing the button, in addition to creating that pulse, exchanging the charges between the charged spinning disks causes a change in that eddy current drag, which results in a very brief change in the moment, the angular momentum of the entire device. All right, I think I'm about ready to shut her down. I have done all I can do for this test.
Well, thank you one more time, sir.
Thank you for joining me for the test, Tim.
Okay, I think that's a wrap. I think